This is my third lecture, and until last time I have talked on the so what we wanted to know is the intercategorical center of the representation category of the quantum group, namely the q-deformation compact Lie group, because this problem is related to the approximation rigidity kind of property, namely property T for tensor category, and this plays an important should play an important role in the classification of subfactors. And so last time I have talked this determination of the all reducible object in the intercategorical center is related to, reduces to the classical, in the classical case, this reduces to the classical problem known as a determination of all reducible interrepresentations of the complex semisimple Lie group. So in this, today I want to talk on just the representation theory of complex semisimple Lie groups, just in the classical case. To give us some intuitive understanding for the quantum case in which I will talk next time. So what I will talk on is representation theory of complex semisimple Lie groups. And this is really a kind of classical object, so some people might have known this. So if you know this, you don't need to listen to this. But anyway, so I want to talk on this today. And especially I want to focus on the low-rank case like SL2C and SL3C for simplicity. Okay, so our setting is as follows. So we start with a complex semisimple Lie group. And we take a maximal compact subgroup. And so our main example is when G is of type A, namely this is SLNC, and we consider the maximal compact SUN inside. And then we take the Lie algebras complexified. So let G be the real Lie algebra of G, namely the complex Lie algebra of K. So yes. And then this is contained in the complexified Lie algebra of this complex semisimple Lie group. So namely this is just twofold direct sum of G. And then we are interested in classifying all irreducible interrepresentation of G. So when you start with unitary irreducible representation of G, then one can restrict this to compact subgroup, and then you can see how this representation decomposes into irreducibles. And then one important theorem by, I guess, Castleman is actually the multiplicity or the each irreducible representation of K arises in has finite multiplicity inside this restricted, pi restricted to K. So has finite multiplicity. Yes. Okay, now, so, and then if you just take the algebraic sum of these irreducible representations, then this is kind of fairly small. This has countable dimension from this. So when you consider algebraic direct sum of irreducible representation K, is well behaved. And so actually, so this does not have an action G. So the action does not integrate with the action G. But still, we have an action of the this V algebra GC, so admits action of the universal enveloping algebra GC. And so again, this does not integrate to the action of G, but you can just take the appropriate completion, and then this extends to the action of G. So this representation of the V algebra remembers the original representation. And
Is that not integrated because G might be a non-simply simply connected?
No. I mean, so this is just dense subspace inside the Hilbert space. So I mean, it's not true that this integrates inside this non-completed space. So anyway, so this and what? Yes. So then this representation remembers the original. This representation remembers the original representation. Okay. And then I want to talk on this kind of representation, and this kind of representation has nice properties, like, so reflecting this property, this representation has a property, namely, if you restrict it to the UG module, if you restrict this representation to this UG, as a representation of UZ, this decomposes into a direct sum of finite dimensional reducibles with finite multiplicities. So this decomposes finite dimensional reducible representation with finite multiplicities. And also we have certain kind of unitarity. Namely, we have an invariant inner product on here. So yes, and so what we want to consider is so if you have these two properties for the representations, then you really get one-to-one correspondence between the irreducible unitary representations of G and the representation with this property. And now I want to omit this property, so I want to also consider non-unitary representations just with this property. So this is, kind of nice, algebraically nice behaved representations, and classify all of the irreducible such representations. And then after that, I want to determine which one is unitary. So I will call this property admissible. So this we call admissible. And so I want to classify all admissible representations, admissible reducible representation, of course, and then determine which one is unitary. And then actually, at least when I saw this one in the first time, the first one seems to be difficult. But actually, it appeared that the second problem is much more difficult than the first one. So in the general real reductive D groups, not only complex ones, the first one is solved by Lagrange, I guess. So it's so-called Lagrange classification. But actually, so we don't have a complete answer for the second one for the general case. And so we only know certain algorithm which determines the unitarity for certain, for each parameters, but for general parameter, so there's no, so one needs to check one by one. Okay. Anyway. So yes, I want to start with the first problem. And so first problem, so there are a lot of research on this. And yeah, so what I want to talk today is the approach based on Bernstein-Gelfand or Enright or Joseph, I guess, coming from the study of category O. So what is category O? So category O is a nice kind of category of the module over the universal enveloping algebra of G, so U of G. So the category O is a category of UG modules such that, so when you recall the highest weight theory or the classification of the finite dimensional representation of the D algebra, then the important thing here is when you consider the joint eigenvalue. Oh yeah, so I want to mention one thing. I want to recall one thing. So G is always generated by a set of generators together with this kind of commutation relation. That's something. And so, yeah, so the important thing here is, so HI is simultaneously diagonalizable. And so EJ and FJ moves, translates some joint eigenspace to another. And actually, so with an appropriate order in the joint eigenvalues, this raises the eigenvalue and this lowers the eigenvalue. And so if the given representation is finite dimensional, there is a maximal joint eigenvalue. And this classifies all, this parameterizes all irreducible representation, all finite dimensional irreducible representations. And what I want to do is do the same thing for the infinite dimensional case. So what I require is only having a highest weight, the maximal joint eigenvalue. So which is generated by highest weight vectors. Namely vectors such that they are annihilated by all of EIs, and plus some finiteness condition. Okay, and the structure of this category is kind of well known. So yeah, basically, what we know is, so there are two special modules in the two kinds of special modules inside this category. Namely, one is the Brahma module. So Brahma module, which is just the universal highest weight module with highest weight lambda in where h is just the span of this guy. So the h star parameterizes the joint eigenvalues of hi's. So you just pick one, and then you can consider highest weight. So the highest weight simply means joint eigenvalue of this d. And then so you consider the highest weight module with highest weight lambda, and then there is a universal one, as well as the irreducible ones, which is the smallest one. Actually, there exists a unique irreducible module with highest weight lambda. Irreducible with highest weight lambda. And then actually, this Brahma module, the structure of this Brahma module is kind of well known. So basically, one can compute the multiplicity of weight spaces and other things just in an easy way. And for this kind of thing, it's a bit more difficult. But in certain cases, we know how this thing can be decomposed. I mean, we know the composition series with respect to these Brahma modules. And actually, it's computed by a kind of combinatorial thing, which we call Hadamandostic polynomial. Yeah, but anyway, so in certain cases, one can really compute.
Excuse me, may I
Yes.
go back to the first part?
Yes, yeah.
If n is equal to 2, for the simplest case, I think
Yes.
maximal compact group is just the S1, isn't it? From Amazon.
N is equal to 2.
2.
SU2 is.
S, that would be S. Wait, okay.
Yeah, so we are considering complex case.
Complex, yeah. Right. Okay, sorry.
So yeah, anyway, so yeah, we have these two modules, and so okay, yeah. So what I wanted to talk is, so basically, so we know more or less most of the structure in this category, so how this category behaves. And then what we wanted to know is this kind of admissible representations, and actually we have a strong connection between this category O and this admissible representations. So for lambda in H star, we consider so the category O with compatible weight with lambda. So this is just the modules with also the weight is just the name of the joint eigenvalues, which weight is in lambda plus p, where p is equals to the weight which integrates to the torus. So torus to torus. I mean, so this is just certain lattice inside the H star. Yeah. Anyway, so yeah, this has some small part of the category O, and we also have so if we consider the admissible representation, we can restrict it to a smaller category, which is admissible representation with central character lambda. I mean, right central character lambda. I will explain this. So what is the right central character? So actually, so the admissible representation is by definition a representation of UG tensor UG. So admissible representation is a certain representation of UG tensor UG. But here, actually, we know I think we know the center of this UG. So if we compute the center of this, then actually this is known to be isomorphic to the symmetric algebra over H. So this is symmetric algebra, which is with the wide group invariant part of this symmetric algebra. So yeah, so let me illustrate this in the case of SL2 or SLN, and the wide group is just the symmetric group acting on the H is diagonal part, so the diagonal matrices by permutation. So that if you consider the symmetric algebra over H, this is just a polynomial, and if you take the invariant part by this permutation group, this is just a symmetric polynomial. And so we know the one-dimensional representation of this algebra, so that one-dimensional or the character one-dimensional representation of S is parameterized by the H star modulo W, of course. I mean, yeah. And then the right central character lambda simply means if you restrict to the center sitting inside the right component is precisely lambda inside here. So, I mean, of course, if you have an admissible or admissible reducible presentation, and if you restrict to this the center, then center needs to act as a scalar. So if you have the admissible, so the B for B via B has the right central character. Lambda, we say when the one tensor center acts as a scalar lambda. So basically, the category of admissible representations decomposes into this decomposes with respect to the right central characters, so that we only need to know each species. And actually, each piece is really category of when lambda has nice property. So probably this has been done by Gelfand, Bernstein, Gelfand, and Enright, and Joseph by independent work. So actually we have a contravariant functor from category O to this admissible, the category of admissible representations. Which is almost categorical equivalent. Actually, not quite, but so what I said here is so for generic lambda, this is really true. Generic lambda, this is true. And for special case, this is not quite true, but still, actually we have a section here, so which goes here to here. So yeah, so which is identity on this admissible representation. So in particular, this shows so irreducible representation maps to irreducible representation or 0. And we really know when this tends to 0. So we already know all reducible representation inside admissible representation just by the classification of the irreducible representation, irreducible module inside category O, which is just this.
Does generic mean dominant?
Sorry, yes. Yeah, lambda should be dominant, yes. Yeah, so actually, so the I forgot to tell this. I mean, so the actually H star has a natural ordering on the real part. I mean, so yeah, so yeah, I will illustrate this in the case of SLN. So when SLN, so the H star, so H is nothing but the diagonal matrices. So which is just the diagonal matrices with the sum is equal to 0. So that H star is equal to Cn modulo 1. And then we can induce a positive structure in the ordering on the Rn over here. Sorry. Yeah. So we say real part of mu is positive if this is increasing. And so dominant means this holds. Simply this holds. Yeah. Or do I need row shift?
Reasonably more than you need.
Yes, yeah, probably I need row shift, right? Yes. Yeah, so, yeah. Yeah, so, yeah. Anyways, yes, we need something like this. Yeah, so yeah, I just wanted to say a bit on the idea of this. So what I want to do is basically, so of course as I said, admissible representation is nothing but a representation of UG tensor UG. So we should have a kind of highest weight theory for this, I mean, philosophically. But actually this is not true. And so what I want to do is basically, so when you have two modules of UG, modules of UG, and you tensor this, and then I want to take the k-finite part of here. I mean, namely the part which you I mean, so this is UG tensor UG module. But when you refer to UG, I mean diagonal UG, then I want to look at this UG acts as a kind of finite way. I mean in the way, I mean this which decomposes into the finite dimensional reducible with respect to the diagonal UG. So I want to take k-finite parts. And if I do this literal way, in a literal way, then the k-finite part is usually 0, so we get something trivial. But I want to take is, so if I want to take the k-finite part, then I can just take k-finite part of completion, of a completion, certain completion of B tensor lambda, or B tensor W. And this is achieved by taking certain algebraic dual. And yeah, so this is, so we need to take the k-finite part of, so passing to the dual, it's easier to take the k-finite part of this guy. And this particularly behaves well when V is projective. And most easiest projective is V is equal to the Brahma module with dominant highest weight. So when V is equal to n lambda for lambda dominant, so this is gives the psi lambda which I introduced in here. Okay. Yes, so at least from this deep result, we get a classification of irreducible objects, irreducible representation, admissible reducibles. Together with another important thing is, so we also know, in certain cases, we also know the composition series by the Barman module. So composition series. And yeah, we know a bit more on the algebraic properties of these admissible representations. Okay. But so yeah, what we were interested in is the unitarity. And actually, at least as far as I know, this theorem does not give any kind of things in the unitarity. So this is just an algebraic functor. So to know which one is unitary, yeah, so at least this solves the first problem. So if we want to know the unitarity, we need to give another construction of such irreducible modules, which is coming from the parabolic induction. So what is parabolic induction? So I want to talk on this in the very easy case, I mean the easiest case, namely the induction from the Borel subgroup. So when you start with the Borel subgroups, which is, so in the SLN case, this is just upper triangular matrices. Inside SLN. And then what we want to do is, from a one-dimensional representation of this Borel, we induce a representation from here to the whole G. So one-dimensional representation of B is parameterized by certain parameterized by P times H star. Again, P is the Contreras dual of P torus, maximal torus inside the compact, maximal compact, which is just a certain lattice inside the Euclidean space. And this H star is just a certain kind of Euclidean space coming from this dual of the span of HIs. And so how can you give this? So if we have a one-dimensional representation of B, this factors through the commutate the arbitrization of B, which is just the diagonal. And the diagonal can be divided into two. So the maximal torus is the maximal compact, just meaning that the diagonal with the entry is modulus 1. And the A, where so we have a direct productive composition like this, where A is the diagonal with positive entries. Yes. And so one can write these positive entries by certain exponential of certain element in the real part of H. And what I want to take is the non-unitary representation, non-unitary character of this guy. So that we have the one-dimensional character of this torus is given by P, and the one-dimensional representation of this tapered by H star. And then we induce the representation to G. So I want to consider the induction from B to G of this one-dimensional representation. So for this, so given a parameter, I want to induce from B to G. And then, so yeah, this is by definition. Yeah, so I need to twist a bit actually. So this is, oh sorry, yeah, I should take the k-finite part. So k-finite part of the function over G, which behaves like this. Yeah. So basically, so the dt to the lambda simply means the pairing between lambda and t. And so this part, so I put 2 over nu, so this is just the one we have nu. But minus rho means, so this is, we need a bit of shift because, yeah, so the rho is, yeah, so rho is the half sum of the, of positive roots, which is equal to the, so in the case of SLN, rho is equal to 2 over n minus 1, I guess. Yeah, so I will explain this, the intuitive meaning of this. So basically, so this rho comes from the density of the volume bundle or something. So basically, if you just mod out G by B, then this quotient space does not have invariant measure. But instead, we can twist the bundle to a volume bundle. And then this rho is half density of the volume or the differential form or something. Anyway, yeah. So anyway, so what I needed to this twist is if we start with the interrepresentation and induce to the G, then I want this is still an interrepresentation. And actually there are another reasons as well, but I will explain this later. So this one is also can be seen as a, so of course this is same as saying the section, C infinity section from a certain bundle. And actually this is also same as saying, so due to the Iwasawa decomposition, we can actually reduce this to everything to the K part as a vector space. So this is as a vector space. Okay. Now, so as I said, so this is just half of the volume bundle. So we have so if you start with as I said, if you start with a unitary character, the induced representation is still unitary. But not only that, if you start with an invariant Sesquilinear pairing between these two representations, then you can induce this Sesquilinear pairing onto the whole thing. So we write this to be L lambda nu. Then, of course, this and the C2 lambda minus nu bar has invariant Sesquilinear pairing. And so this induces a Sesquilinear pairing on this. So there exists non-degenerate invariant Sesquilinear pairing from L lambda nu and L lambda minus nu bar to C, which is, so actually this comes from the integration over K mod T if you view this as this space. So which is actually positive definite. If we regard these spaces as this one as yes, okay, fine. So this induces the, the pairing between the same thing when we identify this space with this one. Now, actually, so this construction has the first glance this construction and this construction of the Bernstein Gelfand and other people are kind of different, but actually we have isomorphism. Again, this is due to the same people as the categorical equivalence. So this parabolic induced module is isomorphic to the image of the Brahma module for I always forget the correspondences between the parameters, and the correct parameterization is this. So at least this parameterization gives you the one-to-one correspondence for all all weight inside H star times H star, and all weight inside the H star, again H star to H star. But so I have put the the lambda is dominant, or I needed to take lambda is a special representative in the wide group orbit. So I needed to take that. So this restricts to the certain weight inside here. And so actually, so what it means is actually there is an overlap for the reducible subquotient of these. So actually, so I need to say one thing. So actually, so there exists a unique subquotient, irreducible subquotient of this with so I need to say minimal k type. So it's so when you decompose into the k fine, the representation of k part, then the when you look at the highest weight, then that there is a representation which has minimal highest weight, which is just a dominant element inside the wide group orbit of lambda. Anyway, so certain nice reducible subquotient inside here. And so this precisely corresponds to from this theorem, one can actually show this precisely corresponds to the irreducible modules. So at least this exhausts all the irreducibles. So this exhausts all irreducibles. And we also know there is overlapping with these. So this is isomorphic to the another one if and only if they are in the same wide group orbit. So there are only finitely many choices of the different parameter with the same representation. And now combining this this classification together with the construction of the invariant linear pairing, one would know this admits an invariant linear form. I mean, not requiring the positivity. If and only if the corresponding counterpart for this pairing is also isomorphic to the original one. So this simply means, so this is, so just from the application of the invariant linear pairing above, so this is if and only if this is isomorphic to this guy, and this is only when, this happens only when this occurs. So this, of course, is same as saying lambda minus mu bar is sitting inside the while group of lambda mu. Okay. And also the v lambda nu admits an invariant inner product if and only if, so of course we need to have this. And so if we have this this implication, I mean, if we have this condition, then we have an intertwining operator, namely, so we have a map from here to here, and so we can consider this as a kind of map on the L lambda nu in certain cases, and this is positive definite with respect to the canonical inner product. Positive definite with respect to the inner product. Of course. Now I want to conclude my seminar by showing the case of SL2 and SL3. So let me start with G is equal to SL2C. So in this case, H is just one-dimensional space, and H star is as well, with a suitable parameterization where if we take the inner product, we say it is 2 over 1 inner. So this should be this parameterization. And then yes, so then the classification result shows, so the admissible induced representation is parameterized by P is equal to 1 over half Z times the whole thing modulo plus minus 1. And yes, so the criterion for the having invariant linear form is the shown as above. And then so what I want to do is compute this intertwining operator. And actually it's possible. So for lambda nu inside this, the intertwining operator going from this to O on the parabolic induction is given by. So actually, so I said, so this intertwining operator gives you an intertwining operator on the level of irreducibles, but actually, so this extends to a meromorphic family of intertwining operator on the this whole parabolic induction, and this is given by certain formula. which I again forget, minus no to mu on so v mu component of L lambda minus mu this goes to kk. So basically we just we restrict to this module to the representation of k, and then we consider the irreducible component at the representation and the component of the v mu part, which is a irreducible representation of k. Then this is actually the scalar multiple like this, and then now it is easy to see when this is positive definite. Of course, this is positive definite if and only if the assigned number is all positive. So this easily gives you the classification in the case of SL2. So basically, so the classification goes as follows. So there are two possibilities. So basically we need to consider this is inside Y group orbit of this. And there are two cases, of course, I mean the Y group element, so the Y group element transforming to this is either 1 or minus 1. So when so I will write this way, when W is equal to 1, then this simply means nu is imaginary. And in this case, then the intertwining operator is just identity, so it's always positive definite. So nu is imaginary. So this is always unitary. And actually, in this case, this is just precisely the case that this representation is induced from this Borel subgroup, unitarily induced from this Borel subgroup. So the another case is when W is minus 1, then nu is real. And in this case, we need to look at the intertwining operators this way, and this is given by this. And this is all positive if and only if nu is small enough. And so unitary, this is always unitary if the absolute value of nu is smaller than 1, I guess, or 1/2, yeah, probably 1. Yes. Oh, sorry, lambda has to be 0. And the second case is so-called complementary series. And actually, yeah, so I want to add one thing. So actually, so as I said, so actually particularly, the case follows from this is only when nu is smaller than, strictly smaller than 1. And when nu is equals to 1, this is really meromorphic. This has zeros on the eigenvalues. And so this is not quite true, but still, if nu is equals to 1, actually the corresponding representation is trivial. So trivial representation is always unitary. So especially this complementary series connects the principal series, which we call, the one unitarily induced from a smaller subgroup to a trivial. And this representation has C0 coefficients. So this in particular shows the Hager property for SL2C. Yeah. Anyway, I want to notice that trivial response to nu is equal to 1. So in the case of G is equal to SL3C, then actually one can show this thing. So in this case, the while group is S3, and so as in this case, right, I want to classify this case by case with respect to W. But actually, an important thing here is if this is equals to this, then we may assume W is, the signature of W is 1, or W is equals to 1. Because so if the signature of W is 0 and W is not equals to 1, so this is just rotation for, rotation, which has the eigenvalue only has the third root of unity. But actually, so this transposes the nu to, so the imaginary part of nu to minus nu, which is impossible for this rotation unless this is stabilized under this while group element. So we always may assume to be this case or this case, and in this case this is already done. So basically this is the same argument as above. So basically this is just the intertwining operator is identity, or in this case this is just unitarily induced from the Borel. And in this case, we may assume up to conjugacy inside the while group. W is equals to transposing 1 and 2. And transposing 1 and 2 comes from, this comes from the flipping this part and this part. So everything occurs inside this SL2 triple. So everything happens inside this SL2. So that actually, this is not really a proof. So we need to argue a bit more on the usability kind of thing. But actually, in this case, one can reduce the things to the SL2C. So at least in this case. So in this case, the intertwining operator is induced from SL to C. And of course, we know that every result in the SL2C case, so we get the result on the SL3C case. So actually, the general theorem by Vaughan goes as follows. So when G is equal to SL and C, then unitary reducible representation is either trivial or unitary induced from a smaller subgroup GL K times GL n minus K. Or the third case is the most interesting case, the complementary series. So namely, so n is actually, n has to be even. So this does not occur in this case. So if n is even, actually there is additional type of representation which comes from induced representation of so this is so A and B are in GL M. So so we consider the block diagonal block upper triangular matrices and maps this to determinant of A to the P for T is between 0 and 1. Yeah, and I should omit saying because this is already unitary induced. So yeah, this type of representation. Anyway, so one can classify all reduced representation, and for our purpose, one can see the property T only from this result. And yes, yeah. So actually, in the proof of this, Vaughan used. So actually, so this type of argument only works for n is equal to odd, and in the case of n is equal to even, actually, we need to argue a bit of the statement like, so if you induce from a irreducible representation when this is irreducible or not. And so we want to get a reducible representation just from the induction. And this is actually not possible from the usual parabolic induction, but we need to use some kind of homological induction kind of technique. And actually, so I don't know how this kind of argument works for the quantum group case. So next time I want to talk on how I can avoid this homological induction technique to classify irreducible interrepresentation of the quantized complex semi-simple Lie group. So yeah, so it's a bit over, but yeah, thank you for listening.
Any questions or comments from the speaker? Then let's thank the speaker again.